In this video, let's understand some of the assumptions that we would generally make whenever we are applying the linear regression algorithm for a given set of data. Now, these assumptions is what we have to ensure whenever we are applying the data on this algorithm. It's not something that by default it will be taken care automatically. So it is something us as a data scientist, we would check whether these assumptions are valid or not, and that will give us the clear idea as whether this linear regression algorithm is suitable for a given data set. Now, in the linear regression model that we have built for a given data set, the R2 score that we are getting is 0.86. Now, this would mean that the model is able to explain about my data set in a better way, I would say. If not 100%, but at least it is able to explain some amount of information from the given data set, which means I would say some or most of the assumptions will be valid for this given data set. So let us look into the important assumptions of the linear regression algorithm and how do we validate it whenever we are working with the data. So first assumption that the algorithm is going to make is there is a linear relationship in a given data set. Now, when I talk about the linear relationship, so here I would assume that the given data set represents the linear relationship between my feature and the target. So in my given data set, let's say we have got the TV, radio, and newspaper. So I would expect that there is a linear relationship between the TV, radio, newspaper with the target column, that is sales. So let's go ahead and validate it. So let me just make use of Seaborn library, and I'm going to say it as import Seaborn as, and I'm going to say df. Okay, my x underscore vars is equal to TV, that's one column, and I'm going to create a plot for newspaper and radio. Okay, so TV, radio, newspaper, and for y I want to have it as sales column. So now if I just execute this cell, so this is how the given data would look like. So from this visualization, we can validate that there is a linear relationship between the TV and the sales and radio and the sales. We don't see much of a stronger relationship between the newspaper and the sales. So that is what we would observe from this plot. So this methodology is called as a visualization methodology to check the linear relationship in a given data set. Now, apart from that, there's another way that is called as creation of the df.describe heat map. So we can just send this df.describe data set into plt.heatmap, and that would actually help us in creating a heat map for us. So I'll just mention it in this way. So sns dot heat map, and here I'm going to say df.describe. Okay, so heat map is directly available inside the Seaborn library, so it's not in matplotlib. So in this way we can go ahead and create the heat map. So normally when we are creating the heat map, it is for the correlation. Okay, it's not simply the describe, it's actually the correlation. So with this correlation values, we will be able to see whether it represents the positive correlation or a negative correlation. We can say annotate is equal to true, so this will enable the annotation, and we will come to know how much linear relationship that we have with the feature and the target. So TV and sales 0.78, that means it's a positive correlation. I would say strong positive. This is, I would say, loosely positive, and this is very loosely positive correlation with the target. So that's how we can check the linearity for the given data set. Okay, now the other assumption that we generally make is, so we will say that there is a mean residuals to be equal to 0. So mean residual is 0. So which means what it clearly states is that whenever I calculate a residual is nothing but taking the difference between my current value and the predicted value, that is the predicted value and the expected value. And if I take the mean of that value, then I will be getting the mean of the residual as 0. So let us go ahead and check the same. In order to check the same, I'll just go ahead and generate the prediction, and I'll take the difference between my y and the predictions. And once that is done, if I calculate the mean, okay, and display the mean residuals for the given data set, see, I've got the value of mean residuals. I would say that here this is minus 0.011, which means I've got the value which is closer to 0. Okay, so this is how we can check for this assumption of mean residual is 0. And the other assumption that we would make is whenever we get the residual value, okay, so in that residual value, so we actually assume that it actually has the normal distribution of error terms. So normal distribution of error terms. So this is another assumption that we make. So we can clearly observe that there is a kind of a normal distribution that we observe on the given data set. Okay, now apart from this, the next assumption that we make is homoscedasticity assumption. It's called as homoscedasticity assumption. Now, when we talk about this homoscedasticity, I can say this is one of the central assumption of the linear regression algorithm. So this homoscedasticity, it actually describes a situation where the error term, that is the noise or the residual value, so like this error term, it actually in the relationship between the independent variable and the dependent variable. So what it checks is whether this residual value is same across all of my independent variables or not. Okay, so if I observe heteroscedasticity, that means it's a violation of homoscedasticity. Okay, so that is the overall idea, team. So we actually we actually have the assumption of this homoscedasticity. So how do we check whether this assumption is true or not? Well, in order to check for homoscedasticity, so we can go ahead and apply the hit quant test. Now, the way that we would generally go ahead and observe, okay, the whether it is homoscedastic or not is, okay, so here we can go ahead and perform this Goldfeld quant test. In order to perform the same, I'll just go ahead and import the library, that is stats models, and if I just go ahead and calculate the same for our given data set, okay, so yeah, if I just show you the code, and if I execute this, I've got the value of p which is greater than 0.05. So, and the test statistic score is 1.32 from this homoscedastic test. Okay, so here in this case, so we assume that, okay, the data that we are dealing with is a homoscedastic. That means if the p-value is greater than 0.05, then I'm going to say my null hypothesis follows, which means in this case the error terms that we have got, it shows the homoscedasticity. Okay, else, okay, alternate hypothesis follows, then this would mean that my error terms are heteroscedastic. Okay, so that is how we check for the assumption. Now in our given data set, since the value of p is greater than 0.05, then I would say that this given data is homoscedastic in nature. Now if you are very new to these statistics and if all these terms are sounding very new to you, do check out the playlist on statistics and probability for data science, where we'll be discussing in detail. Currently, we have got 19, I would say 18 videos over here in this series. So we are updating this video series on a regular basis. Do check out these playlists as well so that you can understand the statistics part in your machine learning journey. So we'll be discussing about the inferential statistics in the statistics and probability for data science playlist. So I highly recommend you to check out the same. Okay, now coming back over here. So we have validated that this given data set is a homoscedastic data set. And the last thing that we would validate is check for the multicollinearity. So here, this multicollinearity helps us to check whether we have correlation between the features itself. Okay, that is the overall idea of checking the multicollinearity. And whenever we are working, so the VIF score that we would get for a given data set, so this VIF score is actually going to tell us, okay, it's going to tell us that like whether we have got multicollinearity on a given data. Okay, so let me just get the data frame. So this is how our data frame would look like. Now on this data frame, I'm going to send in all the columns except the sales column. So now if I calculate the VIF score, we've got the VIF scores as 2.48, 3.28 and 3.055. So which means that all the VIF score that we have got when we apply it on the given data set, then I would say that there is no multicollinearity issue in the given data. So the recommendation is, if the VIF score is greater than 4, then generally we drop the columns and then we will reiterate the process to check whether we have removed the multicollinearity in a given data set. So this was about checking the assumptions of a linear regression algorithm whenever we are applying on a data set. So I hope this video was helpful to you. So do check out the YouTube channel for the complete playlist on machine learning and statistics and probability for data science, which will help you to progress in your machine learning journey. So thanks again for watching, and I look forward to seeing you in our next video.